Any questions for the midterm exam? No? All right. Okay, so now let's come back to the partial differential equations, especially our discussion on the finite element methods. So if you look at the project, you're going to see that the project is actually on finite element methods, which is what we are talking about here. And particularly, the project asks for solving a unsteady partial differential equation using finite elements. So this is something we're going to discuss today. And I mean, if you look at it, the formulation is almost natural. It's like basically once you apply the idea of finite elements, you're going to find out you can solve pretty much, you can deal with the different terms pretty easily. Okay. Okay, so what is the idea of finite elements? The idea of the finite elements is essentially to look at an equation. For example, let's look at this equation. Now we introduce a time derivative term. We still keep our second derivative term, which we have been using in our previous equations, plus this known function f, right? The only thing we are doing differently here is that instead of setting the whole right-hand side to 0, we set the right-hand side to a time derivative of the unknown solution u. Okay, and of course you can deal now. Last lecture we have studied how to deal with different boundary conditions. So this time let's actually just stick to the simplest boundary condition: u0 equal to u1 equal to 0. Okay, you can apply the same kind of boundary conditions we studied last lecture. The Dirichlet boundary conditions, the Newman boundary conditions, right? We can. Okay, so now given this equation, the next thing finite element does is to derive the weak form. So this is actually called the strong form, or the differential form, or yeah. So the next thing is we need to derive the weak form. So how did we derive the weak form when we have a steady equation, when we didn't have a time derivative? Anybody remember?
Integration by parts.
Yeah, but before integration by parts, we did something else, right? We have to have an integral so that we do integration by parts, right? What do we have to do before we do integration by parts? Now remember, the strong form is a differential equation, right? This equation has to hold, has to be true. The equality sign has to hold for every x when x is any number between 0 and 1. The strong form, as you have mentioned, has integration by parts, which means it has an integral. It has integrated over x. So it is not an equation that has to be true for any x, but it is an equation that has to be true for any what?
For any v?
For any v, right, which is not here, right? So v is called the test function. So how did you introduce the v?
Multiply everything by the test function?
Yes, the first thing in deriving the weak form from the strong form is to actually multiply the whole equation by an arbitrary test function v. So if the equation is true, then the equation multiplied by any test function v is still true, right? So if I have any v of x being a test function, okay, then my v times du dx or du dt has to equal to the same kappa times v times the second derivative plus v times f, right? That has to be true for any v, okay? And then we integrate it. We integrate over the whole domain, and that, of course, still has to be true for any v. So by what we have really achieved by this multiplication and the integration, right? So we forgot integral, we have dx. So this is one term, and the next term b times f dx. So what we have achieved is converting a statement that has to be true for any x, as in the strong form, into a statement that has to be true for any test function v, as in the blue statement. Now, this is not the weak form yet, because this is actually not any weaker than the strong form. To really get to the weak form, as one of you correctly pointed out, we need to perform an integration by parts. Okay, and particularly we need to perform integration by parts on the term that involves the second derivative. The goal is to remove one of the derivatives on u and put it on my test function v. That's a step that weakens this differential equation, this equality, in the sense that it no longer requires my solution u to be twice differentiable. Now my u can be just differentiable once, right? I mean, that's an important step, because it is the step that's required for us to be plugging in the kind of hat functions, to be plugging this kind of a piecewise continuous and piecewise linear, piecewise linear and continuous functions into the solution u. Otherwise, it doesn't work, because if I plug in u that is equal to this kind of a piecewise linear functions, what is its second derivative? It is 0 in the linear portion and infinite on these corner points, right? So the second derivative doesn't really work, right, in the strong form, nor it works in this form, in the integrated form. So we have to perform integration by parts to really change it into weak form, and then we can apply the mechanisms of finite elements. So let's do that.